All right, we're going to start talking about different symmetry elements in this video. The main one we're going to focus on here is proper rotations. We will see a little bit of something else here, but basically that's what we're going to focus on here. So for this video, we're going to be talking about examples of the top two symmetry elements here, the identity, which will take all of the slide, and then the rest will be thinking about CN, or rotational axis, in-fold rotations. That's what we're going to be focusing on today in terms of symmetry elements. So the first symmetry element we're going to deal with is that of the identity element, which is denoted as E, that is its symbol for its operation. And this is the do-nothing symmetry element. So let's look at this trigonal planar species that we have here. It has a total of 3 unique substituents around it. So we're going to see something like this will have very low symmetry overall. There is some symmetry here. But one of the things we can see here is a really easy example of identity, whereas, all right, what I want you to do is look at the molecule over here, close your eyes, open them. Now look at the molecule over here. Can you tell if I've done anything? If I've rotated it, I've moved it in any way, shape, or form? No, you can't. So what I did while you weren't looking was the identity element. I did nothing. And we see that it is the same molecule. That's a weird statement here, a weird thing to do, but this comes from the background in mathematics. Really, this is the symmetry equivalent of multiplying by 1. We're not doing anything, but it's definitely part of the theory that we have to have here. This goes into a lot of the understandings of group theory that we'll talk about later on, probably next week. But for right now, this is just, hey, if you do nothing and it looks the same, it is a symmetry element. Every molecule has an identity element. All right, let's move on now to proper rotations, which we're going to give them the label of a capital C with a subscript N. The N will tell us something. N can be basically any integer. It can be 1, 2, 3, so on and so forth. Those are what we'll see in these proper rotations. And they're going to describe how we could rotate a molecule. So for example, down here, I've got a water molecule and I'm looking down the z-axis here. So everything's there in a line. And I'm doing the rotation in this direction here, where now 2 is going to come over and 1 is going to go to the opposite side to give us this structure here on the right. Now again, remember, atoms don't have labels, so take those out of your mind for a second and look at the two structures. You really can't tell anything has been changed after this 180-degree rotation. So that is a proper rotation, which we call a C2. Where does the 2 come from? Well, over here we have a formula that tells us what our N value must be. What we're going to do is take 360, the degrees in a circle, and divide that by whatever rotational angle that we are going over. So in this example up here, we've got 360 divided by 180, which equals 2. So we have our C2 rotation. So we would say that this axis that we're looking down right here, that is a C2 rotational axis. Okay? If we look down here, the next example, this could be something like methane, and we're looking down the z-axis again. But now we see it's slightly different, because now if we rotate, we don't have to rotate by 180 degrees. We only rotate by 120 degrees to get to an equivalent structure. Same idea. Do a 120-degree rotation, and we look over here to the new structure, it looks identical. The only thing that's changed is these labels that I've put on it that you couldn't actually see in reality. If we look here at what we've done, we've got 360 divided by 120, that equals 3, so we have a C3 rotational axis down here. And this is, for example, like an ammonia molecule. So that's how we see proper rotations and how we will label them. Now, when we deal with something that has a rotational axis like we saw here in ammonia, we see something kind of interesting. So let's do this in a couple phases here. So we did our rotation by 120 degrees to get here to our second structure, structure B we could call it, versus structure A and C. So we've gone from A to B, and we have the same structure. So we've done a C3 rotation to get to the same structure. We could do another C3 rotation, again, another 120 degrees, And again, we come to the same looking structure. Again, all we've changed is the positions of these labels here. So we can do multiple rotations of the same thing. So this is now a slightly different operation because we can either do it in 2 steps. We can do a C3 followed by a C3, or we could just do what we call a C2-3, where that 2 is telling us do 2 of the C3 rotations. So this is now the recognition that, hey, I don't have to necessarily go through this middle structure through B. I can just transit from A to C if I did that specific operation. So that's what a multiple rotation would look like. These get a little bit more fun as you start going to higher order axes. So for example, here's something that might be like a square planar molecule, where now we're looking down the z-axis here. And so now we have a 90-degree rotation that we're doing to make these all the same. So let's see, 360 divided by 90 is 4. So we're looking at a C4 axis. So if we start maybe from the middle structure, we can look and see what actually happens as we go around. How do we get to all the equivalent structures? Well, if I just do a C14, otherwise known as just a simple C4, we just move it in a clockwise rotation by 90 degrees. The general way that you keep things straight is always rotate in the same direction. Clockwise is the standard assumption. So our first rotation, we'd be saying for the C1 is to go from this 90-degree rotation to the structure over here. We could do 2 of these C4s to get to the second structure here. But now we notice, hey, this looks like we've just moved from here. We've done a 180-degree rotation, which we saw earlier, 360 divided by 180 was a C2. So we could also say that this is a C2 rotation. Final one that we have up here is the C34, where now we've gone 1, 2, 3 rotations to get us to that final point. So we can look at these in that type of family here. But it's recognition that sometimes we reduce what we're looking at. C24 doesn't exist because it's a C2. We could say the same thing about a C26, which would be the same as a C13. They're identical, so we'll say that we don't actually see a C26, we just see a C3. This comes in from time to time that we'll actually see things like that. Okay? We also run into the times when we can have multiple rotational axes. So here, for example, we've got CO2, and we could look down here and say, all right, if I look down from the top here, I can see my C2 rotational axis because I go around by 180 degrees. There we've got an axis. But we could look at another one. So if I look down the barrel of my CO2 molecule, this is where everything would be eclipsed, where everything looks the same. But think about rotating along that axis. Now, every type of degree that we turn it would not be distinguishable. This is a unique type of rotation, which we call C infinity, because basically we can rotate it by any degree that we want and still have an identical axis. So this leads us to now having 2 rotational axes. Here's one, here's the second rotational axis. So we're going to have to define which one is quote-unquote the more important. This is what we call the principal axis. And that's the one that has the highest order rotational axis. So when I say highest order, what has the biggest number? Infinity is definitely greater than 1. So the principal axis for this molecule is the C infinity axis. Generally, to help, again, keep things aligned for us, we'll say that this is our z-axis. So for carbon dioxide, we would say that the C infinity axis here is going to be the z-axis. And then we could define the x and y off of that if we needed to. All right, so a lot of different types of behaviors can happen here in rotations, but that's what we see here. So as usual, we'll talk about these more in class, and when we have questions, concerns, make sure to bring those up, and we'll make sure we get you clarified. So that'll do it for this video. We'll see some other symmetry elements in upcoming videos. So until I see you next, be excellent to each other.